Hi, welcome. Professor Lamb here, PiPad Mathematics. This is a real popular problem, one I really like. It's called the locker problem, and it's Mark Driscoll and his team, Fostering Algebraic Thinking. They focus in on this problem. This is from their work or from Driscoll's work, and there are a lot of different adaptations. There's a magic card trick out there. There's a couple other similar type of problems, but what this problem does is it allows students to critically think through a problem, think about how they would solve it. Maybe they draw a picture, maybe they make a chart, maybe they act it out. However you do it, you work through this problem, and then in that process you actually model very important aspects of mathematics. Now, kind of the things that I like to focus in on. You can pause the video. You can read through this. I'm just going to read through it real quick. You got 20 lockers. They're in the hallway. It's a scenario that math teachers like to do. Numbered 1 to 20, and Mrs. Mahoney's class returned from summer vacation. They decided to celebrate working off some energy. They came up with a plan. The janitor had closed all the locker doors, and the plan was that the first student would run down and open every door. Then the second student would start with locker number 2 and then closed every second door. The third student started with locker number 3 and changed the state of every third door. The fourth student started with locker number 4 and changed the state of every fourth locker. Fifth student started with locker number 5, changed the state of every fifth locker, and so on until the 20th student had passed by all the lockers. Now, which lockers, here are the questions. Which lockers, I'm going to zoom in on that. Which lockers are still open? Okay, which lockers are still open after the 20th student has gone through? So which lockers are still open after the 20th student has finished? Which locker or lockers changed the most? And then it has this extension. If you have 200 lockers, which lockers are open after the 200th student is finished, and which locker or lockers changed the most? So here's this kind of last one. I'll share with you a little bit. Just you can extend it. It goes into another type of problem. Anyway, so there you are. There's the problem. So let's get to this. So here's a scenario. You got students, Ms. Mahoney's class, and we're gonna go through. And janitors closed all lockers, so I'm gonna go down here and la-di-da-di-da-di-da. I'm gonna change the state of this locker, meaning I'm going to open it. So open, and then whoops, and then go to this one, and we are going to open it, and then we're gonna what are we gonna do? We're gonna open it, and then moving right along, we're going to, yep, that's right, open it. So you can do this all the way down, and you end up with, he's open all the way up to the 20th locker. So first student has opened all the lockers. So now we go to the second student. So we're going to come in, we're going to go to the second student. Take this, kind of zoom here. So there's the second student. And now the second student is we're going to close the second locker, close the fourth locker, close the sixth locker, so forth and so on. And then the third student is going to change the state of the third locker. So if you notice, the third locker here is open. So the third student's got to change the state of it, and it's going to become closed. Then you come over here, and then that's the fourth, fifth, sixth locker. The sixth locker was already closed, so the third student has got to open it. Boop. Okay? And now you are going to end up having to do that for all 20 students. And you can go through and you can open and close, open and close, open and close, open and close. Now, could spend the rest of the video doing that. I'm not. I'm going to zip it on over here, and there it is. Okay, so once you've gotten all of the students through, where they've opened and they've closed, they've opened and they've closed. Now the questions were, the first question was which one was still open. So which lockers are still open? Okay, so we look at our graph and we look here that this locker is open, and this locker is open, and this locker is open. So when we zoom into those, we look to see that right here, this locker was open, and it was the fourth locker. Okay? And then we zoom out a little bit more, and we see this locker is open, and it is the ninth locker. Okay? And so we come over here, and which ones are still open? It turns out the fourth locker is still open, the ninth locker is still open. Oh, I forgot, the first locker is still open. It's sitting right here, still open. Okay? And then, lastly, we had the 16th locker was still open. So locker 1, 4, 9, and 16 were still open. And then, which one changed the most? So that was our second question, is changed the most. Okay? Well, what we can do is we can add all of the different columns up. And we can go through here and we can see that the first locker only changed one time. And then the second locker changed 2 times. The third locker changed 2 times. The fourth locker changed 3 times. The fifth locker changed 2 times. And what you're going to end up finding is once you do all of this, the 12th locker changed 6 times. The 18th locker changed 6 times. And the 20th locker changed 6 times. So the ones that changed the most were the 12th locker, the 18th locker, and the 20th locker. Okay? So those 3 changed the most. And then it asks, well, what happens on the 200th locker? The 200th, or after 200 lockers have gone, which ones are still open? Okay? So which ones are still open? Well, we got to look at a pattern, or we got to look for a pattern. Here are the ones that were still open, and we try to figure out, all right, what makes them open? Or are these numbers special numbers? Do they have anything special about them? And what we look at is these are our square numbers. Okay, so these are our square numbers, our perfect square numbers. So therefore, we list all the perfect squares up till 200. So it'll be all the perfect squares up to 200. And we can make a list right now, but I want to quickly, so the video is not too terribly long, go into one last little thing that you can look at here. So we scooted on over here to the next slide. And one of the things that you as a teacher of mathematics, or you as a student of mathematics, need to look at is what are these, or what is this telling us? What mathematics is going on here? And so I'm going to zoom in a bit here, and I'm going to show you these model the student themselves. When the student moves, when the student is moving here, having some technical problems. It's underneath all this stuff. I can't get to him. There he is. So when the student moves, he changes the first locker, the second locker, the third locker, the fourth, the fifth, the sixth, the seventh. So therefore, when this changes, these are all your multiples of 1, if you will. So 1 times 1, 1 times 2, 1 times 3, 1 times 4. So that becomes your multiples of 1. Same thing with our second locker. Got to get him unhidden here. There he is. That's not cool. Don't do that. I did it. Fiddlesticks. So there's changes the second locker, then changes the fourth locker, then changes the sixth locker, then changes the eighth locker. So 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, 2 times 4 is 8, 2 times 5 is 10, 2 times 6 is 12. So those are your multiples of 2. Let's see if I can get the third guy over here. This is craziness. Craziness. Changing all around. Undo. Alright. There we go. So this was the third. So third, sixth, ninth, 12th. So 3, 6, 9, 12. So the numbers that each student changes are the multiples of that student's number. Okay? And then when you're looking down the columns, if locker number 3 was changed by the first student and the third student, so therefore its factors are 1 and 3. The number 6, it was changed by the first student, by the second student, by the third student, we can go down here, and by the sixth student. So the factors of 6, are going to be 1, 2, 3, and 6. So when we're looking at all of these in the column, each time a student changes the state of a locker, it's showing that student's number is a factor of that locker number. So here on problem number 12, all the factors of 12 are going to be 1, 2, 3, 4, 6, and 12. And the reason why, the last little thing, the reason why our perfect squares, I didn't do that right. The reason why our perfect squares are still open is because they have an odd number of factors. They have 1 times itself, and then let me say that again. The perfect squares have an odd number of factors. The perfect squares have an odd number of factors, which is why they are open at the end. Because they have one factor that multiplies times itself to get that answer. And that's why the perfect squares are still open after you do all of the locker changes. Alright, so there's as best I could, a quick little video about the locker problem and the kind of the elements of the locker problem. Anyway, this didn't have I do better when I have a camera in front and I'm looking at you and talking at you, or talking to you through the camera. But here we are. Thanks for watching.